My name is Rafael Sanchez. I am customer engineer of Google Cloud. I am based in Madrid. And I am here on stage with José Antonio Marcos, who is the head of Smart Maintenance Engineer in Talgo. We are going to talk to you today about what we think is a very interesting IoT use case, because we are going to talk about high-speed trains operating at 300 kilometers per hour, around 200 miles per hour, in the desert of Saudi Arabia. So you can imagine that they have very strict weather conditions there. And these trains operating at 300 kilometers per hour are going to send, or are sending actually, up to 2,000 signals per second to the cloud for processing and for predictive maintenance. So this is what we are going to talk today. So this case study is actually a study around asset tracking and asset management. And before describing the case itself, I would like to start by making some definitions, okay? Knowing that no definition is perfect, I would like to start by defining what is an asset, what is asset tracking, and what is asset management, okay? In order to understand the scope of what we are going to talk to you today. So let me start with the definition of an asset. An asset is a useful or valuable thing or person, generally owned by a person or enterprise, available to perform some utility. Asset tracking is basically around two concepts of this sentence. Asset tracking is around real-time awareness of a valuable thing that we own. Okay, so we have some, for example, in the train, we have some subsystems that we would like to measure, something valuable for us, something valuable for Talgo, and we would like to make some real-time awareness of that particular information. So asset tracking is around understanding this business question that you see on the slide. So where is my asset? So what is the train, for example, or what are certain parts of the train? How does it get to go to the destination? Or what is the current condition, okay? An asset in the context of Talgo is not the train as a whole. It's a series of subsystems that exist in the train and that we would like to make tracking of, okay? So, and what is asset management? Asset management is around performance, is around understanding and managing how an asset is being used. So we are trying to answer business questions here, like if some parts of the train are likely to fail, how efficiently it's being used, or how a particular asset is performing. So the question is, how do we answer those particular business questions, okay? So how do we get the information that we need from these business questions? So what we think is that we will be able to answer these business questions if we collect the right amount of data related to time and space. So if we are able to have tools in order to collect the right information related with time and space, we should be able to answer the business questions before, okay? So so actually the problem of answering those business questions, we have turned that particular problem into a situation where we need to collect the right amount of information, the right amount of data related to time and space. So about timing, we are interested basically in 3 periods of time. We are interested in the now, in the current situation, okay? And this is basically the real-time collection of data. Data which can be associated with temperature, either the outside temperature or the temperature of the different subsystems in the train, or can be, for example, voltage, or can be hydraulics, or can be some particular things in the train that we would like to measure. Past information is just the information we have already collected, okay? So, for example, in the train, this is by the way, the train which is in production in Talgo. This is the line between Medina and Mecca, so this is actually the case study we are talking about here. So, in a train within that route, we are collecting information in the past, and we are storing that information, okay? So this is the past period that we are also interested. And so basically the past period is just information and real-time information that we have collected in the past, okay? So we can do this basically with the same tools. And the future is not information that we are collecting, of course, okay? Because those data does not exist. The future is basically information that we predict. And we predict using machine learning technologies, and we predict using machine learning technology with the data we have already collected, with the data we have collected in the past, and with the real-time data we are collecting. So these are the 3 periods of time, the 3 periods of time that we need to collect information. And this is around timing. And what about the space? In the space, there has been a change over the last years related to space. Basically, there has been a shift from location data into location intelligence. In the past, location was just to put a spot on a map, okay? So to put some train in this case, in a particular map. When we moved to digital maps, it was basically that. But in the last years, there has been a shift from location data to location intelligence, where we add context information around the location. So the location is not just the latitude and the longitude where the train is an amount of information around that particular location where we can get some intelligence from. So in order to do this, in order to collect information from time and in order to collect information from space, we need to have the right tools. We need to have the right tools in the cloud. And Google Cloud has very interesting tools in order to collect information relating to time and space. For space, we have our Google Maps platform for enterprises, okay? And for timing, we have a series of processing data tools that allow us also to collect information regarding the time, real-time awareness, past information, etc. We can find these tools as a separate products, okay? Tools for ingestion, tools for processing, tools for visualization, but also in Google Cloud, just to put you an example of some of the products that we have also products that combine timing and space information into just one. And I would like to show you just one of it, which is the BigQuery GIS. I suppose that you know BigQuery. BigQuery is our data warehouse product. It's a serverless platform to make queries over large data sets at a very competitive costs. It's a serverless platform, and we have introduced a new feature which basically allows us to visualize latitude and longitude information within BigQuery. So we can build SQL queries with geographical information inside, and we can visualize that information directly in the product itself. Okay. So this is a sample of a product that combines timing and space information, and Talgo is actually using some of the Google Cloud products that allow to collect timing and space information. Okay, and this is the use case we are going to talk to you about today. This case study was published 1 month ago. You can access to the case study in that URL, cloud.google.com/customers/Talgo, where we describe the case study in detail, and actually with some quotes from Jose Antonio. And well, we describe all the technology that we were using in that. But I cannot think of a better person to tell us more about Talgo and to tell us more about why Talgo have chosen Google Cloud than Jose Antonio Marcos, who will tell us more about the case study.
Thank you, Rafa. Good afternoon, everyone. First of all, let me introduce you to Talgo. Talgo is a high-speed manufacturing and maintenance company founded in 1942. In the early days, Talgo designed trains with very innovative features, which is the backbone of the company. Actually, Talgo started to build trains, light aluminum trains, in USA in 1946, using the aircraft technology, aluminum, because that technology it wasn't yet available in Europe. 77 years later, Talgo is leader with this technology in different countries. Nowadays, Talgo is developing high-speed trains, running about 220 miles per hour, 350 kilometers per hour. For example, this is the new train, high-speed train in Spain. This new project for Abril for high-speed 2 in UK, Abril, UK. And the high-speed train for Saudi Arabia, which is the case that I'm going to present you afterwards. Regarding Talgo technology, the main features comparing Talgo trains with the standard ones are, for example, independent wheels, natural tilting, aluminum-like cars, lower floor level, automatic gate change, and articulated cars. As a general information, Talgo main figures are as follows. Talgo has footprint in 44 countries, more than 4,000 vehicles, 77 years of experience, and we are performing more than 1,000 million kilometers per year. So that means 4 times the distance between the Earth to the Moon every year, just to keep in mind. Now we get into the case. Nowadays, high-speed trains maintenance operation is a complex, very complex, and high-tech. We need to solve different technological challenges. For example, safety first, no questions, very high speed, more than 220 miles per hour or 350 kilometers per hour, reliability, about 1 million miles between stops, between delays, availability, 100% of the trains running in the track, and maintenance intervals between stops every 30,000 miles. So how to do it? In order to reach these challenges, we had to work with new maintenance technologies. For example, CBM, condition-based maintenance, in order to anticipate the failures of the train that may result in lack of availability and reliability of the train. To apply condition-based maintenance, we need to develop algorithms. These algorithms need a lot of data in order to work with machine learning. So in order to get this data, we had developed a real-time monitoring system using Google Cloud Platform. The architecture you are going to see afterwards. Rafa is going to show you. So now we get into the successful case, monitoring system for Saudi Arabia high-speed trains. This project had several challenges. For example, extreme weather conditions, high temperature during summertime, more than 120 degrees Fahrenheit. Extreme weather conditions, sandstorms, the geography. Another challenge was to understand how to send big stream data from the train to the ground control. And we had to decide how to do it, not for this train, but for the future trains. So what were the challenges that we had to deal with? We had to deal with data transmission, ingestion capacity, processing capacity, and storage capacity. All these challenges. How did we solve it? We had to select from different options. On-premise, we need a huge investment, other cloud solution, and finally we decided to go with Google Cloud. Why? Because Google Cloud offers us different advantages. For example, unlimited scalability, connectivity, massive storage, streaming data, and machine learning for predictive maintenance. How is the process? The train is sending data in 3 different ways. Using UDP, datagrams, streaming data, live streaming data. We are sending more than 2,000 signals per second per train. Also, we are able to download the whole database when the train goes to the maintenance facilities through Wi-Fi. I'm talking about 2 gigabytes per train per day. And also, we are sending the batch alarms. Every 10 minutes, we are sending the main alarms and the main events from the train. So once we have the data in the cloud, ingested and stored in BigQuery, we are able to track the trains using Google Maps, also performing real-time monitoring, and we are doing machine learning and predictive maintenance using our application, Talgo Tesla. The acronym of the Tesla is Train Efficient System Logic Analysis. So now we are going to see a video with the example of the application that we developed. using Google Maps. So here we can see the trains, the location of the trains. We can find out the problems that they are sending in real time. We can select different data, different parameters to understand which is the problem that the train is having in order to get insight of the data. So we can choose from different trains, different countries. Now we are going to see an example with a video of the other application that we developed using Google Cloud. This is real-time monitoring. We are monitoring different parameters of the train, the speed, and also we are able to monitorize in real time every single signal in order to analyze what is going on and to improve the reliability and availability of the train. Okay. So now Rafa is going to show you which is the architecture of this case.
Okay, thank you, José Antonio. So I'm going to show you now the architecture which is in production today in the Saudi Arabia lines. Okay, so basically the architecture that generate all these videos and graphs that we have seen before. So I'm going to describe the three architectures that are in production today. One is about real-time monitoring, the other one is about historical analysis, and the third one is about event data management. So let me start with the first one. This is the one about real-time monitoring, where the trains operating at 300 kilometers per hour are sending 2,000 UDP datagrams per second to the cloud. So they are sending this by using GSMR technology. Okay, so the GSM is a public telephony standard, and there is a variant for railways application, which is the GSMR. Actually, the R is for railway, and this is a very well-known railway standard. Okay. So the GSMR has the capabilities, has very interesting capabilities. For example, it operates at a different frequency band than the public GSM. So therefore, there are no interference with the public GSM technology. It can also operate with trains up to 500 kilometers per hour. So it's good enough for this particular application. And also, normally, when you design a high-speed line with GSMR, you have antennas all over the lines, which guarantees you the coverage even inside the tunnels. Okay, so that's the reason why the GSMR is a good enough technology today for this particular application. So we are using GSMR, and then over a VPN, over a VPN, we are sending the signals to a managed instance group in Google Cloud Platform. Actually, we are using an internal load balancer. An internal load balancer here, which basically balances the traffic to the different Google Compute Engine machines. So after that, all the traffic is being sent to a queuing system, to Cloud PubSub, and then it is going to App Engine for processing. Okay, so we are not using Dataflow on that particular application. We are using a Node.js application built on App Engine, which is basically decoding the UDP packets. And then the packets are going for visualization in real time to another App Engine application, which is the one that makes the visualization. One interesting capability is that we are also using a database here in order to store all the real-time information that we are receiving. Okay, so while there is here a real-time path using a WebSocket that visualizes directly all the real-time information into a graph, we are also storing, Talgo is also storing the historical information coming from this stream. So to summarize this particular architecture, so we are collecting the information using GSMR with UDP datagrams. Then this goes to an autoscaler group built with an internal load balancer and a managed instance group. Then it goes to PubSub for collecting all the information, App Engine to decode the UDP datagrams and extract the useful information, and finally, another App Engine application for visualization. You may notice that on this particular architecture, there is no Cloud IoT Core, which is one of the products that normally appears in an IoT application like this. And the reason is the following. When we designed these particular architectures, the train were already built. So you can imagine that a train like this takes a lot of time to be designed and to be manufactured, and there is a lot of security inside. I mean, you cannot just come here and put a software there or a hardware there, and because Talgo is making a very strict homologation process for hardware and software. So basically, we didn't arrive with enough time in order to install our Cloud SDK and install all the capability or an MQTT client on the train in order to be able to talk to Cloud IoT Core, because Cloud IoT Core, as you know, requires MQTT or HTTP and requires also TLS 1.2. So we could not install all the right software libraries in order to deploy that on the trains. But the future architecture that I will describe you afterwards, we are including Cloud IoT Core, of course. Okay, so that's the reason behind that. Basically, we didn't have time in order to install and homologate all the software and to pass all the homologation tests required by Talgo. Because again, as you can see, I mean, this is a very strict device. Okay, so it's we need to pass very strict homologation process, and we cannot just go and do whatever we want. So this is the architecture about real-time monitoring. The next architecture is about historical analysis. In this case, the information is sent when the train is stopped for maintenance. Stopped for maintenance at the Talgo facility. Okay, so the train is stopped. This happens normally once every 15 days or once every 20 days. And when that happens, the train is sending 2 gigabyte files per day of operation to a local compute which is installed on the Talgo facility. So again, you may ask, why a local compute here? The reason is the same as before. We didn't have time to add the necessary software on the train, our Cloud SDK, etc., in order to send it directly to GCS. But in the future architecture, this is included. So these files are, again, these are non-SQLite database, which are 2 gigabyte size per day, which is sent to a local compute. In this local compute, we have GSUtil installed. Then the local compute sends the information to cloud storage in GSUtil. And then when that happens, there is a cloud function which is triggered. And this triggered will launch a data flow pipeline to process all the SQLite database. So the SQLite database goes to BigQuery for storage and visualization, and to an App Engine for visualization of the historical data. So to summarize, we have Wi-Fi data when the train is stopped, which is sent to a local compute for and cloud storage. Then we are sending it to cloud function. A cloud function is triggered for extraction, then data flow, and then App Engine for visualization. And the third architecture, which is in production in Talgo, is the one about event data and alarm data collection. So this is not real time, because this is actually a batch type of architecture, because we are sending alarms every minute, and we are sending events every 10 minutes to the cloud. So what is an event in this particular context? So an event is triggered where certain conditions are met. For example, imagine that a temperature is higher than 40 degrees, plus that the voltage is exceeding whatever value, plus the train speed is at 250 kilometers per hour. If the three conditions are met, then an event is triggered and is sent to the cloud. But we are not collecting events and alarms in real time. We are collecting events and alarms in batch mode. So alarms every minute and events every 10 minutes. So the way we send this information is again via GSMR using a VPN over TCP to a compute engine machine. We don't need auto-scaling in this case because the amount of traffic is relatively low. Then this is sent to cloud storage for storing, and then this information is sent. There is an application which is basically collecting the information from cloud storage, and then sent to PubSub, cloud data flow for processing, BigQuery, App Engine, and finally visualizing here. The visualization is happening in a tool called Cassandra, which, by the way, has nothing to do with the Cassandra non-SQL database. Okay, so it's a customized tool for Talgo. I mean, the name has nothing to do with that. So to summarize, so the events and alarms are sent through GSMR in batch mode. This is sent in cloud storage, and then from cloud storage, we start all the processing and visualization using the standard pipeline processing with Dataflow, PubSub, and BigQuery until the visualization. Okay, so until now, I have described the three architectures which are in production today in the Saudi Arabia line between Medina and Mecca. From now on, I am going to talk to you about the new architecture that are going to be designed for the new lines that Talgo is going to deploy all over the world. So this architecture has been designed and has been agreed with them over the last months. And basically, the general view is this one. So we have designed this in mind according to the requirements that Talgo had. And Talgo had requirements not only of data scaling, of course, because there are going to be more and more lines with this architecture, and this requires an escalation in terms of data, but also this has been designed because there are other devices where we need to collect information from, okay? So, and these are not only the trains. So, for example, if you see here, these are structures which are equipped across the lines, okay? So these are like wayside inspections that are collecting information from the train as the train is passing through this particular structure, okay? So this is not the train itself. These are devices, okay? So you can see here, devices that are put in the line, and they are getting information from the train. Also, in the train itself, we are interested in collecting not only data information itself, we are also interested in collecting multimedia files. For example, images and also audios, because audios are very interesting in order to detect problems in the train. Okay, so if you listen to, for example, the engine of the train, you can make predictive maintenance according to that particular audio. So multimedia files are also very, very interesting, and the new requirements include the collection of this type of information. So this new architecture basically includes three new elements. The first element is Cloud IoT Core. So Cloud IoT Core are now is going to be included, and we are going to use MQTT in order to send the messages to the train, and also we are going to use TLS 1.2 in order to make the transportation. We are going to add also some processing at the edge, so some processing in the train itself. So now we are going to design some customized software in order to be equipped inside the train, and also hardware that we are going to put inside the train in order to make, for example, well, machine learning, predictive maintenance, and some other stuff. And finally, the third piece we are going to add to the architecture is Cloud ML Engine in order to make all the training and inference required with the data that we are collecting, and also to be able to download the models that are trained in the cloud to the devices in the train itself. So these are the three key elements that are going to be added. Let me go a little bit deeper into these two, into the Cloud IoT Core and the cloud and the edge processing. The Cloud Machine Learning Engine, I think, is a very well-known product from Google Cloud, so I will skip that in this presentation. So let me focus on these two. So Cloud IoT Core, I mean, it's a product that is already GA, and basically it provides two capabilities. It's a message broker for HTTP and MQTT messages. It provides also security by implementing TLS 1.2 mandatory in all the communications, and also provides device management capability. So somehow it's an inventory of all the sensors and subsystems that are tracked in the train. One of the characteristics of Cloud IoT Core is that it's completely serverless and has a unique global access point. So no matter if Talgo is operating in Saudi Arabia, in the US, or in the United Kingdom, all the information is going to be sent to Google Cloud through the closest data center. And this is going to happen automatically without Talgo intervention. So this is about Cloud IoT Core. And one of the most interesting parts is the processing we have designed for the edge. In this slide, you can see two parts, one in the left and one in the right. The right is just basically a summary of the cloud piece for machine learning. So I am going to skip this part because it's more or less obvious and does not contain all the details of the previous slides. I'm going to focus more on this particular part, on the left part, which is the part which is going to be equipped in the train. So in the train, we have an Ethernet bus, which is here, okay? So this Ethernet bus is basically the bus which is collecting all type of signals in the train. So it's a very, is a very important part of the train because it's collecting all kinds of signals. Some of these signals are going to be sent to the software we have designed in the edge and are going to be sent through a path protected by a diode. Okay, so this diode is going to prevent the signals from going from the software to the bus. Okay, so it will only allow signals going from the Ethernet bus to our software part. Then this piece of software is going to be designed for Talgo, and it's basically a software based on a microservices architecture. So we are going to design a container-based solution for this particular part. And basically, well, this software piece has, first of all, an interface software, which is, this is not a container. This is basically, well, a firmware which is collecting the information coming from the Ethernet bus. And then this is going to send information to the container that will receive the signals. Then this container must exist mandatory. The other container that must exist also mandatory is what we call container 0, which is the one which is sending the information to the cloud, sending and receiving information to the cloud. So this will send all kinds of events, alarms, variables, etc., as well as it will download any machine learning models coming from the cloud. And then optionally, we should have one or more extra containers for different tasks. For example, we can have a container in order to select the variables that we are going to send to the cloud. Or for example, this container can also make some machine learning activities if required. The design based in container is basically a little bit open on this particular part because we can design a software with 3 or 4 containers, but basically the architecture is based on containers in order to facilitate isolation and in order to facilitate scalability. So for a high-speed train like this, security is very important. I mean, you can imagine that these trains cannot fail, okay? So these trains, everything must work perfect, and a containerized-based application fits in this particular requirement. So that's the reason why we have designed a microservice architecture for this particular part. So this container solution is going to be built on a Linux OS operating system, and then below that we will have the hardware part. And the hardware part initially is going to be designed with a CPU. I mean, basically with a CPU, and optionally we are going to host a space for TPUs, because we think that the use cases for this particular application may require TPUs, especially for the multimedia processing. So that's basically the design that is going to be implemented in the train. So a microservices architecture built on software and hardware that needs to be, of course, homologated by Talgo. And for the hardware part, the edge TPU, I mean, just for your information, we have recently released through our partner Coral some TPUs already available in system of modules architectures. Okay, so you can see. If you go to the webpage of Coral, okay, this partner of Google has released some hardware cards with TPU inside with different hardware schemes. So you can use a system of module, and also you can use PCI accelerators to be placed in any card. So there are different options to install this kind of hardware. So with this design in mind, how the architectures look like. So the architecture for the new speed trains look like the following. For historical analysis, the changes are that we are going now to, well, we are still using Wi-Fi, okay, in order to send the historical databases to the cloud. You may notice that there is no local compute anymore, okay, because we have installed the Cloud SDK and GSUtil in the train, so the train will send data directly to cloud storage. Also, the train should be equipped with 5G, and the reason for that is because imagine that the train, for whatever reason, is stopped in the middle of the train. So we should be able to send information very quickly to the facility for processing. So 5G should operate also as well with Wi-Fi. And the amount of information we are going to send are not only the SQLite databases, also the multimedia files are going to be sent to cloud storage. So the rest will be more or less the same. A cloud function here will trigger a function that will start a data flow pipeline in order to collect all the information that will be sent to BigQuery for visualization and potentially to cloud machine learning to train a new model if required. And the second, so to summarize, so Wi-Fi or 5G data is going to be sent to cloud storage and then to cloud functions for extracting the information to cloud storage, and then processing and to data flow and machine learning, and finally to visualize. And the architecture related to real-time processing and event data management are going to be merged. So the two previous ones are going to be merged into just one. And in this particular case, we are going to use MQTT with MQTT and also the batch information for events and alarms. And this time we are going to use data flow in order to unify the processing of real-time and batch. That's the reason why we unify both architectures. So all the data will go to Cloud IoT Core, then Cloud Functions will trigger a function in order to be processed by PubSub and go to data flow and App Engine. I would like to highlight something about this architecture, which is the serverless approach, and especially the usage of data flow here for processing all the information. This is very interesting for Talgo because data flow allows scaling up and scaling down. So during the day, trains are operating. So, and you need to process a lot of information. Data flow can scale up in order to process more information if required. But during the night, when trains do not operate, basically data flow can scale down and Talgo is going to pay nothing for the processing, okay? Because data flow allows scaling up and scaling down automatically. So that means that you can, during the day, while the trains are operating between the different lines, trains are going to send information and data flow is going to scale up. But during the night, when trains are not operating, data flow is going to automatically scale down and Talgo will not pay anything for the data flow or for Cloud IoT Core, okay, or for Cloud PubSub. So this is the advantage of a serverless approach. This is an advantage of a serverless architecture like this. Okay, so all the solution is going to scale up and scale down automatically. And I make a remark on the escalation down automatically. I mean, Talgo is not going to do anything during the night in order to switch off the machines or switch off the workers in order to pay less. So this is going to be done automatically by Google Cloud. Another advantage like this is that data flow is going to unify the processing model of batch and streaming. So actually, the same prod is going to make both type of processing. Okay, batch for events and alarms, and processing for real-time information. So to summarize this architecture, so this is we are going to send information in batch and streaming to the cloud. That will go to some of them to the IoT Core, and then data flow will provide this serverless approach with an automatically scaling up and scaling down whenever it's required, and data store and App Engine for visualization. So in this architecture, we have machine learning, and actually Talgo is working today on some machine learning models that Jose Antonio is going to explain in a second, that are actually being worked today. So now I'm going to pass the word to Jose Antonio because he's going to explain us a machine learning predictive maintenance case which they are using today in the Saudi Arabia line.
Thank you, Rafa. Okay, now I'm going to talk about the Talgo Tesla application. This application has been developed using machine learning to predict the failures of different systems of the train in advance. As an example, I'm going to explain you how the application is capable to predict the failures of the axle bearing in advance, at least 3 weeks. Okay, it works in this way. The axle of the train, you can see in the top part of the screen, has 4 bearings. Each bearing has a temperature sensor. Every temperature sensor is being monitored in real time. So the neural network using Keras library and TensorFlow backend predict the temperature for each sensor every second using the other 3 real-time temperatures of the other 3 sensors plus the outside temperature. Once the temperature is predicted, the application is comparing this predicted temperature with the real one. If the difference between them is higher than the expected, the application provides an alarm. And also, the most important thing is that we are able to predict the failure in advance at least 3 weeks in order to avoid to have some failure in the train during the service and to do the maintenance as predictive maintenance. Okay, in this screen, you can see in the upper part the general overview of the train with the axles. For example, this axle, this bearing, has an alarm. That means that this difference between the real temperature, which is the blue, with the calculated one is higher than the limit. So the application gets an alarm to be fixed for the maintenance people and for the engineers. And now we are going to see a video with all the information that I presented before. So we are performing real-time monitoring in very extreme conditions, weather conditions, Kazakhstan, or in the middle of the desert in Saudi Arabia. We are sending the data from the sensor, the train, to the cloud in streaming, 2,000 signals per second, from different trains, different countries, to the cloud. So once we have the data there, we are able to analyze the data with our expertise, and we can get insight from the data in order to improve the safety, the reliability, and the availability of the train. And like in F1, we had to perform the maintenance as needed using machine learning and real-time monitoring to improve the safety, reliability, and maintenance. And now, what's next? To connect not only the train, but also all the assets that Talgo has in a global IoT platform using our application Talgo Tesla and Google Cloud solution. This, for example, we are developing a new equipment called Talvi, capable to inspect the train automatically when the train is running up to 100 miles per hour in the track. This equipment has 3D scan technology and visual artificial cameras to inspect the wheel parameters, the site integrity of the train, the brakes, the frame, and also the roof inspections. So all this we are able to do thanks to the IoT cloud platform. So that's all. Thank you. And I hope that it has been interesting for you and useful maybe for your business case. Thank you.